right, yeah, so we said the basic two methods of image generation are modeling and rendering, which is where we want to look into as part of this course. So the rest is just a little an overview of this that also should prepare you a little bit for the practical assignment. There are two basic methods that we usually approach, that we use in computer graphics to approach this problem of creating realistically looking 3D images on our 2D screen. One is ray tracing, the other is projective methods. We will talk about ray tracing at the end of this lecture in the last two sessions, but just as an introduction, a little idea of it. Just as an introduction, the basic idea of ray tracing. Ray tracing is basically, in ray tracing, we assume that we have a 3D model of our scene, of our virtual reality, and we want to bring that 3D model now on the 2D screen. Now, this 2D screen, you can basically see this as a large glass window that you look through into this virtual world, which is then behind your screen. And that means that if you're looking if you draw a line from your eye to one of the pixels on the screen, you have to make a decision what color is the pixel on the screen that represents the object that is at that position that I see when I look through this virtual glass window into this virtual world. And that you can calculate, of course, if you have the 3D representation in a mathematical description in your virtual world, and you know it is at this position when I place my glass window on my screen here, and you have your observer's position, and you look into the pixel, and then of course the color of that pixel is defined by the color of the object that you see when you follow that line or that ray that you shoot from your eye through the pixel towards the virtual scene. And the first object that you hit is of course the object that color influences the pixel on the screen. It's a little more complicated in real life, of course, because the object can, for example, be also transparent. Then the ray goes through the object and shows you, for example, the glass, which also contributes to the color, but also the object behind it, where the ray hits it. If there is a distortion in the glass, your ray gets a little distorted. Another thing that influences it is, of course, the light that you have on this position. If you have a light coming from the left or a light coming from the right, that influences how you see the color on that pixel. And with ray tracing, here is where the physics comes into play. We know from physics how light is reflected. So for example, if we have a flat surface and we are looking at it from that angle, then we know from physics, so this is our eye, we're looking at it, then we know from physics that this angle here is the same angle as, no, the other way around, if light hits a surface, then it is reflected at the same angle. So we know that here we have the maximum intensity of the light. If we move a little bit away with our eye, the angle changes and we have a lower intensity of our light. And we can use that to calculate it. And that's how we're doing it with ray tracing. We follow this ray. If it is a transparent object, it goes through the object, maybe a little distorted, and then hits another object. And then we know we have to take this color and this color here to calculate the color of the pixel here. If it is a solid object, it is reflected, then maybe it is reflected by another light, and here we probably have a light source, and then we know that light source and the reflection of this object influence the color, together with the color of the actual object, influence the color of the pixel here, and we can calculate it. And that is the basic idea of ray tracing, and this is also why ray tracing produces such realistic images, because it considers the whole light conditions. It considers from the whole virtual scene how light is reflected from other objects and how this reflection influences the pixel or the point on the object that you see or that you want to draw in that one pixel or that one point on the screen. So this is, of course, the big advantage of ray tracing, that it considers this so-called global illumination as part of the algorithm. But of course, this global illumination is an iterative process. In a worst case, one of the rays can bounce between all the objects in a scene. So for each pixel, you have to look and to process all the objects that you have in your virtual scene. And if you think about these very complex models that, like these two characters we saw from Monsters Inc., that have a lot of are made out of very small polygons or triangles, then you have a lot of objects that you have to consider, and that means that's why ray tracing is usually very, very slow. Of course, there are approaches to make it faster. There is a trend towards real-time ray tracing, but in generally, ray tracing has the major characteristic: it produces very realistic images, but at a very, very slow speed. And this is also why 2 years ago, when we introduced the focus on game technology in the bachelor program, we stopped with the ray tracing, because before that, ray tracing was done in the practicals of this course, and then we switched to the more shader programming, which is the second approach, which I will talk about shortly. But first, some examples from ray tracing. So you see here, these are images that are purely created with ray tracing. It's very difficult to see the difference between this image and a real photo. Of course, if you look carefully, you see that this is probably, or you can guess that this is not a real office, but a computer-generated image. And the major reason why you see that it looks basically too perfect, too shiny, which is also a characteristic of ray tracing, that it produces this really perfect images, that they are so perfect that they are too perfect for real world. They look too shiny and not really at some points not or ray tracing is very often, you also see this example, this very nice reflecting spheres that you have, because these are the things that you can do very, very well and very easily with ray tracing. But they're very difficult to do with these projection methods, or more difficult to do. Yeah, these are some examples from the programming assignments from that time, like 2 or 3 years ago. And like I said, we now switched to shader programming, which is more related to, which is based on the so-called projective methods, which is the second most popular approach for creating images and graphics. Here the idea is basically the other way around here. Of course, we also assume that we have an observer here in front of the computer screen, which is also sometimes called a virtual camera. And we have a computer screen which can be seen as a window into a virtual world. But instead of thinking about, okay, how does this pixel on the screen look like when I look at it from my position, we're looking at the scene and say, okay, how does the scene project towards the observer when we want to have the scene projected towards this position of the observer? So we look, for example, at an object here like this triangle, and then we say, okay, our observer is at this position. So if we take that object and think about how it is projected towards this observer, towards the eye of the observer, how does he see it? It follows these lines that we draw from the vertices of the triangle to the position of the observer, to our virtual camera. And then, of course, the intersection points between those lines and the screen window are exactly the points where the vertices of these objects in a 3D world appear on our 2D representation on the screen. And this is then where we have to draw the triangle. So we're dealing here then with the vertices that describe the 3D object instead of the individual pixels that make it up. And we project those vertices to the screen, and then we know these are the vertices of a triangle, and we can draw the color of the triangle. And you see here, this does not consider the reflection. Of course, we can also calculate light reflections, and we do that, of course, to create more realistic images. And you could also do this by considering all objects around you, like we do it in ray tracing, but you have to explicitly calculate that, whereas in ray tracing it is an integrated part of the algorithm that does this automatically. Here we have to put in some extra effort on to create this global illumination that considers all light influences, which is why these images created with projective methods very often do not look as realistic as ray tracing images, but they have the advantage that they are much faster. Because we are dealing here with the objects, we are calculating the visual representation based on the objects, whereas with ray tracing we go through all the pixels, and for each pixel we can go recursively through all the objects, because all the objects can influence the light on that particular pixel. Good. So we'll go into the details of this later throughout this course, so don't be frustrated if a lot of this sounds a little high level or too much now. It just should give you a general high level understanding of the procedure, and then we will talk about the unique steps individually later. Good. Yeah, and of course, this is faster because of the whole procedure, but it is also faster because it is usually hardware supported, which is why it is, of course, if it's hardware supported, it's usually faster, and this is why it's usually used in computer games, and that is, of course, why I think most of you have a high interest into it. And this is why we are going to do this in the practicals. So these are some examples from the practicals. Of course, you see we're not going to implement a very advanced fancy graphics here, so but we will do a lot of like nice effects and test them and implement them. If you're not impressed by that, even better, because then you should be motivated to create something even better, and I can show it then next year. Good. So yeah, so in the remainder I just want to go through a process called the graphics pipeline, or I want to go through this process of projecting on a very high level using this phrase of a graphics pipeline. And the idea of that is basically just to give you an idea of this process and also to introduce certain terminology, because especially when you do the practicals, you will read a lot of technical terms that at first might confuse you because it's just too many new terms. But what is behind those terms is actually quite simple, or the idea behind it is quite simple, which is why it's important to get a high-level overview of it. So when we're dealing with graphics, especially with projective methods, we usually talk, a phrase that you very often hear is a so-called graphics pipeline. Now, a graphics pipeline is more an abstract phrase that describes this kind of process. Depending on in which context you hear it, people interpret it kind of differently. Because, for example, actually these are two. I looked it up in the book if there is a definition for graphics pipeline in the book, and there is not really a definition, but there is an informal description. In fact, there are two informal descriptions. The first one is from the introduction, which says 3D graphics pipeline is a special hardware or software subsystem that efficiently draws 3D primitives in perspective. And then in the actual chapter where I got this image from and where the actual description of it is, it says a sequence of operations transforming 3D models into pixels on the screen. And you see the last one is a very abstract high-level description of this process, whereas the first one already refers to more concrete things, more like hardware or software implementations. But yeah, so the major thing here is, of course, that it describes the process of going from 3D representation, abstract geometric representation of the scene, to a 2D representation on your screen. So that means the actual pixels, whereas here you have the geometric description of your scene. And this process is usually summarized as under graphics pipeline, and there are, of course, it is used sometimes when you have a hardware implementation of that. There are also software implementations of the graphics pipeline, or like we do it here in the course, you will very often deal with it on a very abstract level, which basically means it's just a phrase that describes this whole concept, this whole process. And the reason why it's called a pipeline is that the phrase pipeline is very often a concept in computer science that is very often used, for example, in relation to parallel processing. If you had a lecture or will have a course about parallel computing, you will very likely hear the phrase pipeline very often, because a pipeline is usually, or the concept of a pipeline in computer science is generally characterized by a sequence of processing steps where the output of one step is the input for the next step. Which is why it's very popular in parallel processing, because if the output of one step is the input of the next step, you can have a separate processor for each of the steps, and after one step is done, the next processor can already start by processing the next data unit, which in graphics, for example, would be a triangle. So if you want to draw a scene or a character with 1,000 triangles, you can do the first step, then you process the result to the next step, and then you start already drawing the next triangle with this first processor. This is how you can easily parallelize it. But from an abstract level, it is only important to know that we have certain steps, certain sequence of steps, and the output of one step is the input for the next step. So what are the steps that we need to do when we want to project our 3D abstract geometric representation onto the 2D screen to create this pixel raster image of the 2D the 2D representation of the 3D screen, the first step is, of course, to compute the 3D geometry. And for that, we're usually using a graphics API. And this is then, of course, usually the part where I remind people, or that I use to illustrate the little problem that I have with this course, that there are people with so many different backgrounds. Let me just ask you, who knows what an API is or has heard the term before? Okay, more than expected. Who doesn't really know what it is or has heard it but has no really clue what it is? Okay, much less, but of course there are also a couple of people who are not afraid or ashamed to raise their hand, but there is no need to be ashamed. Like I said, it is obvious that we have people with different levels, and that's like a good example to illustrate that. Like I'm pretty sure a lot of people say, well, oh my God, he's explaining what API stands for. It stands for Application Program Interface. A lot of people might think, oh, what kind of a lame course is that, when he explains all those basics here. But there are also, of course, a couple of people, if I just write API here, they are like, what the hell is he talking about? So just as a reminder, if there are some parts of the course where you don't feel challenged enough, there is enough opportunity to do more advanced stuff, for example, in the practicals. So then really focus on the part that is more suited for your needs, and be patient with the people who have to catch up. For the people who have to catch up, we are aware that there are people here who have very little pre-knowledge. If I'm going too fast, or if you need more information, don't feel afraid or ashamed to ask. Ask me questions. It's no problem at all that I can go into more detail, or I can refer you then. Go to the teaching assistants in the tutorial or in the practicals. They can give you more detailed information about it. They can help you work on your deficits. So just to make you aware also that this is really something I have to kind of find the right balance here in the course, and it's not always very easy. And I'm saying this because every year in the evaluation I get some comments on, well, this course, there was too much, it was too fast, and it was too, I couldn't catch up with it. And then I get these other comments who say, well, this was just so simple, there was all very high level, only scratched, and geen diepgang is a word that I often hear sometimes, or read sometimes. So I'm aware of that. The problem is just, I cannot solve this problem. I can only explain it to you and encourage you to deal with it a little bit yourself. Good. All right, now go back to the graphics, so interesting part. Graphics API. So it's basically a library, a set of collections of programming commands that you can use to describe your graphics, your 3D, and they're usually called so-called primitives. Primitives are basically the subset of the geometry that is supported by the API. So for example, if you have a hardware pipeline, then very often the hardware only supports triangles. And the triangles are then the primitives that you use to build your more complex 3D models. And the reason why triangles are supported by hardware, first of all, they are very easy to process, but most importantly, they are very powerful. In a lot of situations, we can draw very complex models by just using triangles, which is why a lot of computer graphics are basically just modeled with triangles. So even if you want to draw a circle, you can do that by just having very, very small triangles. So that doesn't look like a circle at all, but that is because I'm very bad at drawing here. But you get the idea that you can use triangles to create a shape that has no similarity with a triangle at all, but you can do that in a way that it looks like a circle, if you do it with a computer or if you have better drawing skills. Good. And so like I said, this is, for example, if you want to do it with a hardware pipeline, then you have an API that allows you to access this hardware. And that, for example, is in the Windows environment, it's DirectX, or more specifically Direct3D. DirectX is the more general API that covers all kind of media-related stuff. And Direct3D is then the 3D part of it. Or on Linux and Mac environments, you use OpenGL. And then you use a so-called shader language, which allows you to do more detailed programming of the actual graphics hardware, and that is what you will do then in the second and in the third assignment of the practical part of the course. And here in the lecture, like I said, we will focus more on the concepts and the theory behind it. Good. Yeah, so that is of course the first thing. You need API to specify your geometry, and then you put the geometry from the 3D description that you have on the 2D screen. And this is done in a process called perspective projection, or here in this case it's called vertex processing. That's another thing I have to warn you about. I'm usually using the phrases and the terms that are in the book because the course is on the theory, so I'm focusing on the book also to make it easier for you when you read the book to make the transition to the lecture, whereas the practicals focus more, use the terminology of the actual APIs, which are then implemented by organizations, or in case of DirectX from Microsoft, by companies. So they use slightly different terminology sometimes. So for example, here I use later the term fragments like it is used in the book. I think the shading language from Microsoft uses fragments in a different kind of way, have a different interpretation of it. We were talking about should we synchronize it better, but the point is if we use the book and if we use the API, it's just no way because they are just different, and it's also for you important to learn and to get experience and to be able to switch between and to understand that different people use the same different terminologies to describe the same thing to make that switch. So I just need to warn you about that. Good. Yeah, so the next step we have in our pipeline is the vertex processing. So what we basically do, for example, with the triangle, we take the 3 points and project them onto the 2D screen in a process called perspective projection. And when you program it, you just have to call the respective function. When you do it in the course, we will then learn also what is going on behind that function when we call it, which is basically a matrix multiplication that does this projection then. And we will cover that very soon. Good, then we have our triangle projected on the screen, but we still have this abstract 3D geometry of the triangle. We have the 3 corner points of the triangle, and we have information about the color of the triangle, but we still don't have the triangle drawn. We only know where the 3 vertices are, so we have to then make the step to drawing the triangles onto the screen to really decide which are the pixels where we put color on and which are the pixels that we do not put color on to represent that triangle. And that process is called rasterization. And this is where the term fragments comes in. I already used the term pixels before because I assume that everyone is familiar with what a pixel is. A pixel is basically the smallest unit that you have on a screen. So in this, if you have this raster display with a matrix or a grid, then one grid cell is 1 pixel. So that's the smallest point that you can access and control on your screen. And they use here the term fragment because it's they use it in a more general, generic way. Because if we are dealing at it at this level, we the pixel is just the one final point on the screen, but the fragment can be also other points. So for example, if we have a transparent triangle and another triangle behind it, then of course both contribute to the final color that we have in the pixel. And this is why the projection of them is not called the pixel, but it's called the fragment. And the pixel that we draw then is the combination of these 2 fragments, which leads then to the next step, which is the fragment processing and blending, which is then, for example, if you have a transparent fragment, then you have to combine the 2 colors in an appropriate way to draw your final pixel. Or if the triangle is not transparent, then you have to make a decision. Okay, which triangle is in front of you? So which is the triangle that you see actually on the screen, and the other one you have to ignore because, of course, if it's behind it and if it's not transparent, you don't see it from that perspective. Good. Now, of course, this kind of process, there are also other things involved, like I said, the light calculations, consideration of light influences and all these kind of things, the texture of the object, like if you have a wood or a plastic or a metal, light gets reflected differently, it looks differently. A red piece of wood, piece of metal looks different than a red piece of paper or plastic. And this is all summarized under the phrase shading, but it's not like one step in the pipeline, but this is a step that is included in various stages of the pipeline depending on where the calculation is more easier. Another thing we have to do is a so-called clipping. I can show this easily at an image here. If you have, for example, here, if you look at this area that you see here, now if you have here a triangle that goes a little bit out of the area that you see here. When you project that on the screen, on this 2D plane that represents the screen, you get these 2 points here on the side. But to draw it, actually, you need these intersection points here. So you need to do one step, which is a clipping, which is also located somewhere here in the pipeline, but it's not indicated as a separate step, but it is part of this. I think the clipping is part of the vertex processing when you do the projection to calculate these 2 corner points here, these intersection points here, to be able to draw the triangle here appropriately. Good. Yeah, and we will talk about all of these as part of the course. I'm just mentioning them now because they are also, they will appear in the practical assignment, so to give you a high-level overview. And don't be frustrated right now if it's too much, if you don't get a complete understanding of all of it. This will come over time, and also you're very much encouraged to ask the teaching assistants and also ask them about questions if you don't understand a term like this. So don't feel afraid that, yeah, I don't know anything, I'm afraid to ask. The less you know, the more you should ask. Good. Any questions about this pipeline stuff so far? No? Any other questions? Good, then we come to the overview. So like I said, the first couple of lectures will be, so that was done, almost done. The first part will be pretty much, so this is pretty much the pure mathematics. Then the texturing is a little bit something that we kind of moved ahead a little bit because you need it for the second programming assignment. And then this is then the second part, which is then covered by the second exam. So here we have the midterm exam. And this is then the more detailed graphic stuff. And then you see also why these 2 exams have a different characteristic. The first one is way more on the mathematical side, whereas the second one is way more on the application and the algorithm side. But you need the mathematics from the first part, of course, for it. So it is not really uncommon that the mathematics students do very well in the first and then very bad in the second one, or worse in the second one. And that the computer science students do not that well in the first part, but then do reasonably well in the second one and then still pass the course. So also don't be frustrated when it doesn't work out that well at the beginning, but be aware to catch up with it. Wait, I can show this with the schedule here. Yeah, so this is the schedule online now that illustrates it, the practical assignments. So the tutorials and the assignments are online today. And like I said, the tutorial sessions start on Thursday. There is always usually 1 week, or if there is a holiday, it's a little extended. But there are basically 4 time slots where you can go to the tutorials and ask questions. And the assignments, they are online now. Deadline for the first one, which is a tutorial, is in 2 weeks. Like I said, should be very simple for most of you. But don't use this excuse, the deadline is in 2 weeks and it's very simple, so we don't have to start this week, as an excuse to really push it. But do it now, and if you're done after 1 week, the second assignment will be online then in the second week, and then you can already start with that. And then you see this is much more difficult and much more work to do. And if you then you can have a better estimate about how much work it will be. Good. So, are there any questions about this? No? If not, then, like I said, the other events start on Thursday. If you go to the conference, then the next opportunity is Tuesday. If there are no more questions, then we close a little earlier today. So I see you again on Thursday, and those of you who go to conference, have fun.